Hello everybody. Today I am going to share some of my knowledge in single stage amplifiers. As we are focusing on the VLSI domain, so our whatever this discussion will solely focus on the MOSFETs as a primary level. Okay, and day by day it will go to the bipolar design and the BiCMOS design. Okay, now the basic concepts of an amplifier. We know that the transfer characteristics of an amplifier, that is the relationship between the input signal and the output signal, is given by, that is yt approximately will be given by the alpha naught plus alpha naught xt and some higher order terms. Okay, and the relationship is given in the figure right side, and for sufficiently narrow range of x, okay, we can approximate that equation as yt equal to approximately will be given by alpha naught plus alpha naught xt, where alpha naught is nothing but the operating point, that is a DC bias point of that particular amplifier system, and alpha 1 is the small signal gain. Now why I am saying that this is it is a small signal gain? See that yt is given by approximately alpha naught plus alpha 1 xt. Okay. Now if we take the differential at the both side, we get whatever, that is delta, you can say the capital delta yt would be equal to delta alpha 1 into delta xt. Okay, this is the nothing but the increments or decrements at the input and output side respectively, and from that we can readily show that delta y by delta x will be nothing but this alpha 1. So we are saying that alpha 1 is the small signal gain. Then why it is small signal? So that is written in the last line. Sorry, there will be not a question mark, it is a very greater than mark, that is as long as alpha naught is, it's a problem with the math type. Okay, so as long as alpha naught is very greater than alpha 1 xt, the bias point is disrupted negligibly and gives the linear relationship between the increments or the decrements at the input and the output side. Now there are different aspects for the performance of an amplifier design in the analog design, and it is given by some octagon, and it is shown in the slide, and there are different trade-offs between any two performance, that is it may be trade-off between linearity gain, it may be gain and the input output impedances, it may be the power dissipation and the voltage swings. For given specification, we can sacrifice any or one of the performance, that is we can sacrifice the noise performance of that particular amplifier and we want to increase the voltage swing at the output, or it may be we want to sacrifice the speed in with respect to the linearity of that particular amplifier. But for the any given specification, you have to define this octagon very specifically, and you have to remember this octagon not only, but intuition and your analog design experience will boost your performance in design respect. Now some fundamental issues. As I have said already that we are focusing at the primary stage on the MOSFET only, so I just give you some review on the MOS device capacitance and model parameters, MOS spice model and possible layout pattern of MOS. As I think it is already covered in your previous classes, so just I want to say some whatever the capacitances of a MOS devices. See in this slide, that is that there is a, whenever it is in cutoff region, that is whenever the MOS is in cutoff region, then there will be no channel from source to drain. Okay, and for that case there will be a whatever in gate to source there will be a capacitance, and from gate to drain there will be another capacitance, gate to bulk will be capacitance. Okay, but in linear region there will be a channel from source to drain, and for that case the gate to bulk capacitance will be nil, and for that case we will get only the gate to source and gate to drain capacitance will be divided into two equal capacitance, that is half C1 and half C2. And another main view is that in the small channel case there will be some overlap capacitance between the gate and the source and gate and the drain, which is given by that C2. Now in saturation region, as there will be pinch off between the gate and drain, there will be no capacitance between the gate and drain, that is that there will be no C1 term and only the overlap capacitance C2 term will be there. Okay, and this you have to remember in your high frequency analysis of your amplifier. Now I want to again review that whatever the current equation for the MOS devices. Okay, now there will be, you know, there will be three main region of a MOS operation, that is the cutoff, linear region and the saturation region or saturation mode. And in linear region, that is defined by the whatever the relationship or whatever the value of VDS and VGS minus VT. Whenever the VDS will be less or equal to VGS minus VT, then it will be in the linear region and the current equation will be given by that equation, you know. And then the saturation mode, that is whenever VDS is greater than VGS minus VT, and that equation will be given by that. Whatever we know that whenever the channel length will be big, then there will be no dependencies on the VDS and the ID. That is, ID is not will be the function of the VDS at the saturation region, but whenever we go to the small channel, then there will be channel length modulation effect, and there will be another term, that is 1 plus lambda VDS term, and this lambda is inversely proportional to the length. That is, whenever the long channel device, then lambda will vanish and we will get only the kn prime by 2 W by L in VGS minus VT whole square. Now there is a main fact in your class, I think you know that ID will be given by some beta factor than VGS minus VT or so, and this beta is will be kn prime into W by L. Okay, but this W by L is our prime factor in our design, because we only can vary this W by L only. Okay. Now some useful parameters, that is the GM, G0 and the GMB. GM is nothing but the transconductance, that is whenever we vary our VGS taking constant VDS, we will get this type of curve, and the change in delta ID with respect to delta VGS will give this transconductance parameter, that is GM, and GM will can be calculated from that particular equation, that is in saturation region we can write that ID equal to half mu n C ox W by L, this VGS minus VT whole square. Primarily we can ignore that VDS term, and from that we can readily calculate the delta ID by delta VGS from this equation, taking VDS equal to constant, it needless to say, and from that we can readily calculate this whatever that the GM will give, that is it may be mu n C of W by L into VOB. One more thing, what is the VOB? VOB is nothing but the VGS minus VT. In different literature it may be used as a V on, and it is nothing but the overdrive voltage of a particular MOS in the saturation region. Okay, and there are different equation for the GM that you can see in my slide. Three main equations, mu n C of W by L and VOB, and it may be current dependent or it may be current and VOB dependent. Okay, and which formula should be used in our design perspective, it depends on the circuit condition or it depends on the analysis. Okay, now then is the output transconductance. Output transconductance will appear from our previous slide. See that the ID VDS curve, if in the saturation region we neglect the channel length modulation, then there will be no delta ID by delta VDS, because there will be no dependency of the ID on the VDS, so we can get nothing. That is, it maybe you can say that it is infinite. Okay, that is delta ID by delta VDS, sorry, 0. And from that case, if there is a channel length modulation effect, then there will be a finite slope of that particular curve in the saturation regions. So for that case, it will call the output transconductance in the saturation region. Okay, and it will be given by G0 equal to delta IDS by delta VDS. But see, in the linear region, that is in ohmic triode region, we can see that there will be a finite slope always. Okay, so as there is a dependency on the ID and the VDS, so this is nothing but it is not the output transconductance of that particular amplifier. In this region, mainly the MOSFETs are used as a switch, and that resistance, that is delta IDS by delta VDS, that is conductance, primarily set as the on resistance of the switch. Now there is the GMB, that is backgate transconductance. It is if mainly there are 4 terminals of a particular MOS, that is the source, drain, gate and bulk. Whenever the MOS are fabricated, there is a very thin field oxide below that particular silicon, and for that case, yeah, there will be some MOS behavior from the back side also, and for that particular case we will get there is a dependency on the bulk to source voltage to the performance of that particular MOS, and for that case we will get the GMB. If the bulk and the source are short circuited, then there will be no voltage in that respect to bulk and source, and so for that case we will not get anything dependencies. But if the source and the bulk voltage are different, then we will get this type of transconductance parameter, and it will be given by GMB equal to delta ADS by delta VDS. Okay, but you have to don't remember that big formula, that is GM into gamma by something. You have to remember only the eta GM, and that is the eta is some process dependent parameter. Okay, that is the VBSQ. Phi s is the 2 phi f. You know what is the 2 phi f. Okay, now I am going to the small signal models of the MOS. I think you have already covered what will be the small signal model in your previous class, but still I am giving some overview of this model. What is the whatever I said, that what will be a GM, GMB and R naught, and for that particular case you see this is the low frequency model where we have neglected all the capacitances, and from this circuit we can from KCL or in this case it is use the KCL, and from that case IDS is be given by GMVGS plus GMBVS plus 1 by R naught into VDS, where VGS is nothing but the gate to source voltage. Okay, and then now this is the small signal high frequency model. In that case we cannot neglect all the capacitances. Okay, and this for that case there will be some gate to source, gate to bulk, gate to drain capacitances, and one more thing, that is the what is the source to bulk and the drain to bulk capacitance. Now the structure or the schematic of the MOS device is like this. Okay, yeah, here we are seeing that the N plus region and N to N plus region of the source and the drain, and there is a P region which is nothing but the bulk region, and we know that if there is a N and P region, there will be some junction capacitance in between them. Okay, so we can say that there will be some junction capacitance between the source and the bulk and drain and the bulk, that like this, and this is the capacitances that is called the CSB and the CDB as shown in the figure that is in the slide. Now what will be the design flow whenever we are trying to design a single stage amplifier? If I know the circuit, then from how we will approach our to meet our specification. This is nothing but we have to find the what will be the DC operating point, then small signal analysis of that particular amplifier, then high frequency analysis if we need. Okay, now these are the three main single stage amplifier, that is the common source, common drain and the common gate. In this slide you have to see whatever is the input, whenever in which place we are giving the input and from where we are taking the output. This is the main thing for these three amplifiers, and whatever the application of this amplifier I will say. Okay, now this I will start from the common source amplifier. There are different types of common source stage. This is the with having the resistive load whichever is shown in the right side of this slide, and there will be diode connected load, it may be the current source load, triode connected load, and last one is very important, that is the source degeneration common source amplifier. Now main question will be why we should use these different types of common source stage to meet our specification. That may be different specification, it may be the our linearity region of that particular amplifier will be this, our output resistance will be this, our output drive capability will be that, our voltage swing will be that. From that particular point of view we will go to different designs, that is maybe a resistive load, diode connected load, current source load, or whatever source degeneration. Now see this, firstly this resistive load. Firstly I already said that we have to fix whatever will be the bias point. For this case we have to analyze that circuit in the DC mode, that is a large signal analysis of that particular MOS amplifier. In the CS stage, we primarily give the input at the gate of that particular amplifier, that is a MOS, and we will take the output from the drain of that particular MOS. Okay. Now, if we want to analyze in the DC domain of that particular amplifier, we should vary the input voltage of this that is a Vin of this amplifier. If we want to increase, that is from 0 to VDD, what will be the output voltage we have to find. Okay. Now, let us start that Vin will be 0 and the range will be, that is Vin will greater than 0 but less or equal to VTH, that is VTH is nothing but the threshold voltage of the MOS. Okay. Now, if is Vin in this region, then the main thing is the MOS device will be in cutoff region, so there will be no current through this MOS device. So, the Vout will be connected to the VDD and output voltage is nothing but the VDD, that is whenever the Vin is up to VTH. Now, whenever the Vin is greater than, that is something greater than, it may be 0.1 volt, they are greater than VTH, then it will on. Okay. Now, in which region it will on depend on the output voltage, that is VD, because VD will select that what will be the operating region of that particular MOS in the on state. That is, if VDS is greater than VGS minus VTH, then it will be naturally in saturation region. So, as we have seen that VD before that VTH, Vout is nothing but at the VDD level. So, we can say that it is nothing but in the saturation region, that whenever the MOS will be on, it will be directly in the saturation region. And what will be the output voltage? Will nothing but Vout equal to VDD minus is ID RD, and ID is nothing but the saturation current of this particular MOS. That, so we can write that half mu n Cox into W by L VGS minus VTH whole square into RD. Again we are neglecting the channel length modulation effect. Now see that there is a relationship, that is Vout is nothing but the VDD minus ID RD. Whenever we want to increase the Vn, then the current will be increased. If the current will increase, then VDD minus RD, ID RD will decrease. Okay. So the output voltage will also decrease with the increase in the Vin. And how much level of the Vin this transistor will be in saturation mode, we can readily calculate that. That is, whenever the output voltage equal to, that is Vin minus VTH for a particular Vin, then the MOS will be in the linear region. That is, we can say that whenever this Vout prime, we can write that Vout prime equal to Vin prime minus VTH, then this MOS transistor will be in the linear region. Okay, then we can extrapolate, or you can say that we can draw whatever will be the characteristics, that is the transfer characteristics of that particular transistor, that is Vout versus Vin, and we can see that this particular point is nothing but VTH, and this particular prime is nothing but the Vin prime. In this region it is in the saturation region, in this region it is in the cutoff region, and in this region it is in the triode region. Now, in the very first slide I have said that the amplifier system will give the amplified output whenever this delta y by delta x, that is equal to alpha 1, is greater than 1. Okay. Now, from this graph, that is the transfer characteristics of this resistive load CS stage, seeing that in this particular saturation region of operation of that MOS, we are getting this delta y by delta x is greater than 1. Okay. Another aspect that is very important, that is in this region and in that region, you are seeing that whenever the Vin is low, the output is high, and whenever Vin is high, that is output is low. Okay, and this is very important application in the digital domain, that is nothing but the digital inverter. Whenever we are operating our transistor in the cutoff and in triode region, it is in the digital domain, and whenever we are using in the saturation region, that is nothing but the analog amplifier. Okay. Now we want to go in the diode connected load, but why should I go the diode connected load? Then see that in that particular characteristics, that is we have to have the small signal analysis to know why should we go to the diode connected load. Okay, now I want to draw the small signal equivalent circuit of that particular MOS. Firstly, we have to define whatever will be the AC ground of whenever we analyze that particular MOS in a MOS or whatever this amplifying system in a small signal model. AC ground is nothing but at a particular node is there, if there is no AC variation, that is it may be that we are applying the input voltage superimposing the DC operating point, something that is DC operating point will be in anywhere in this particular saturation region, and this in this saturation region we fix our bias point and superimpose an AC signal. Okay, now with this AC signal the output voltage will also vary, as ever we said that there will be the increment and decrement in the input and the output side simultaneously, but there will be some node where the voltage will not increment or decrement. That is, we can say that two nodes, that is VDD and the ground, the node voltage of that particular node will not vary, and so these nodes are nothing but the AC grounds. Whenever we analyze that particular circuit in the small signal model, then we take that particular node as a ground, and which is called nothing but the AC ground. Okay, now we want to draw some small signal circuit of that particular resistive load CS stage. Now in this is nothing but the, very specifically say it is very much approximated small signal circuit, and in that circuit we are seeing that Vin is applied at the gate with respect to AC ground, and we are applying also that is from the RD we will take the output, that is nothing but V out, and we have to calculate whatever will be the gain, that is small signal gain is V out by V in. We can easily calculate that from our circuit theory knowledge, and see that is from through RD the current will be nothing but the GM VGS. Okay, then what will be the output voltage? Output voltage is nothing but the will be the GM minus GM VGS into RD, and VGS is nothing but V in, and so we can say that V out will nothing but V out by V in is nothing but minus GM RD. Whatever we have neglected here is the output resistance, that is R naught. Why? In our first primary case the R naught is not our primary focus. Now if we take that R naught, what will be that effect? The effect will nothing but the gain will be minus GM RD parallel R naught. Okay, and another thing is the GMB VBS term. Now see that in this particular whatever that is amplifying system, the source is grounded, and naturally for all the NMOS cases the bulk also grounded, so there will be no VBS volt, that is VBS will be 0, and for that case GMB VBS will be 0, and the current is 0, so we don't need to draw that particular GM VBS voltage control current source. Okay, and from that we are saying that getting that gain equal to GM into RD parallel R naught. Okay, that is the transconductance parameter into the output resistance. Remember this all the things, that is gain is nothing but the transconductance parameters of that particular amplifier and the output impedance of that particular amplifier. Okay, why I am saying that not output resistance, so I am saying output impedance. Whenever I will go to that high frequency analysis, there will be some capacitance. Okay, for that case we will get a capacitive effect or so in that particular case, and so I am saying that this is nothing but the impedance, output impedance. Okay, now this gain AV is our we can neglect again the R naught. This AV equal to minus GMRD. And what is the GM? Can you remember that what is the GM? GM is nothing but delta IDS by delta VGS with VDS taking constant. Okay. Now what will be that? It is nothing but 2 into mu n Cox into W by L into ID into RD. And what is the ID? RD it is nothing but voltage across that particular RD, that is called VRD by ID. And ultimately the gain equation is converted to this. There will be three main terms by which we can alter the gain of that particular amplifier. The main term, three main terms are this W by L. As I have already said, this is the main thing in your hand. Another thing is VRD, and last thing is the ID. Okay. Now VRD we can change by changing the resistance RD, and how we can change ID? ID is now we can change only by that. We know that we can change by the bias current, because ID solely depend on the overdrive voltage VOB, and VOB is nothing but the VGS minus VTH, and VGS is here the bias point, and we can change that bias point because that is the very big region. Okay. Now what will be the effect if we change these different terms, because there should be some trade-off between that. Okay. Now if we increase this W by L ratio, then the gain will increase, but if we increase the W by L, what will the effect? From our fabricating that is whatever you can say the layout pattern of that particular MOS, if we increase this W by L, then the capacitance at the gate will increase, and it will affect on the high frequency performance of that particular amplifier. I will go in next, and next we will increase the VRD. If we want to increase the VRD taking ID as a constant, then RD we have to increase. But if we increase the RD, then see that output voltage is nothing but VDD minus VRD. So if we want to increase the VRD to have the gain more, so the output voltage swing will be less, because this is nothing but VDD minus VRD. And last term is nothing but the ID. We have to decrease the ID. Okay. If we want to decrease the ID taking VRD as a constant, so the RD will have to be increased. Okay. As the ID is constant, so there will be no effect on the output swing. Okay, sorry, our ID is decreased and RD is increased, so there will be no effect on the output swing, but effect will be the speed of that particular amplifier. It may be in the digital domain, or it may be in the analog amplifying region. There will be some delay that is dependent on the RC delay of that particular amplifier. So there will be different trade-offs if we increase the gain by increasing W by L, by increasing VRD, or decreasing the ID. Okay, that is another effect there will be, that is GM term is depends on the input. As I have said that ID is nothing but the dependent on the VGS, that is a bias point, and VGS is nothing but the input voltage. Okay, so we have to design a circuit where the gain is weaker function of the input voltage. So we go to this diode connected current source load, triode connected load, etc. Now I want to go to the diode connected load. This is the two different diode connected load, that is first one is nothing but the NMOS, and last one is nothing but the PMOS diode connected. Now we have to use it as a resistor. Okay, now how we can say this is nothing but a resistor? So we can readily approach to our decision by analyzing it in the small signal model. Okay, now see that the voltage gate and the drain of that particular MOS is shorted and directly connected to in MOSFET directly connected to the VDD, that is nothing but the AC ground. So what will be the small signal model of that particular thing? We want to know this input resistance for that particular NMOS, this. So in that particular case we have to impose an voltage, that is Vx, and I have to calculate that Ix. From that case we can readily calculate that is Rin is nothing but that Vx by Ix. Okay. Now this Ix is nothing but the Gm Vgs into Gm Vbs plus Gm Vbs, but what is Vgs? Vgs is nothing but this voltage. Okay, that this. And what is now Vgs is? Vgs is nothing but minus Vx. And what is the Vbs? See that this is grounded, this bulk. Always for NMOS case this is grounded, for the PMOS case it is directly connected to the VDD. Okay, so what will be the bulk to source voltage, that is Vbs in that particular NMOS is nothing but this again Vx, because the Vx is imposed at the source. So Vbs is nothing but also the minus Vx. So we can say that Ix equal to minus of Gm Vgs plus Gm Vbs, and substituting the value of the Vgs and Vbs, we get that it is nothing but Gm plus Gmb whole into Vx, and for that case we getting Rin is nothing but 1 by Gm plus Gmb. Okay. Now I go to the diode connected load. This is the diode connected load CS stage. Firstly, we directly go to the DC analysis of this particular stage. We see that whenever this Vin is less than Vth, the lower transistor will be off. But what will be the output voltage then? It is not a passive resistor, that is RD. It is an active resistor. We are saying this is an active resistor because we are using a active device. So it is called the nothing but the active resistor, and there will be, as it is diode connected load, so there will be nothing but the Vth, that is the diode voltage. In that case, in our diode we say that it is nothing but the Vt. In our MOS, which is in diode connection, we will call that diode voltage is Vth, that is the threshold voltage of that particular MOS. So the output voltage is VDD minus Vth in whenever the input voltage is less than Vth or greater than equal to 0, or greater than 0 and less than equal to Vth. Okay, and whenever we increase that Vin, we will get same characteristics as in the resistive load CS stage, but the maximum voltage is not here is VDD, here it is nothing but VDD minus Vth. Okay, now I have already said that the DC gain or small signal gain is nothing but the transconductance parameter into the output resistance. Okay, now for this particular MOS, that is the lower one, the transconductance parameter is nothing but the Gm, and what will be the output resistance here? I have already calculated. If it is an M2 transistor, this is an M1 transistor, so this is nothing but the Gm1, and what will be the output resistance? This is resistance. This transistor will whatever see in this direction, that is nothing but the Rin of that particular diode connected load, and which is already calculated that Gm2 plus Gmb2. Okay, it is nothing but Gm1 by Gm2 plus Gmb2. In this case, we have neglected the effect of the channel length modulation. To simplify the calculation, this is nothing but this. Okay, here we see that if these two MOS devices, that is these NMOS devices having the same length, that is same width and length, that is W by L, so we can easily see that this is GM1 and GM2 approximately given by the GM2. Okay, so we can take common from the lower side, and this is eta term. I have already said that is GMB is nothing but the eta into GM. So we can take common in the lower side, and this will be given by that. Okay, this is, I say that this is GM1 by GM2 into 1 by eta. Then the main thing is what is the GM1 by GM2, because 1 by 1 plus eta is constant and it solely depends on the process. So what is the ratio of the GM1 by GM2? It may be equal or anything else. So how can we decide that? The GM1 is nothing but 2 mu n Cox into W by L1 into ID. The current through these MOS will be the same because they are in series, W by L2 into ID. Hence, this is nothing but the ratio, square root of the ratio of these two devices. Hence, the gain dependencies on the input voltage is nil here. So we can say that with the loss of the maximum output voltage, that is the VDD, we get this type of relationship at the of the gain, which don't depend on the input voltage, and it is solely depend on the W by L ratios of these MOS devices, and which is very important to get to meet a particular specification. Now there is a problem with that particular eta, from where it is coming, that is GMB is nothing but eta into GM. Okay, now if we use that PMOS diode connected load in place of the NMOS diode connected load, whatever is happened, I want to draw. See, this is the PMOS diode connected load. Here the bulk is connected to the VDD and source also, so there will be no GMB effect. Okay, there will be no GMB VBS term. So for that particular case, what will be the gain? The gain will nothing but, directly we can write that this is nothing but GM1 by GM2. And what will be the ratio then? This will be mu n W by L 1 by mu p into W by L 2. Here the mu n and mu p, that is mobility dependency, will come here. Again, at the operating point, that is in the both the transistor will be saturation, because the source and the drain are connected, drain and the gate are always connected. So VDS always greater than VGS minus VTH in the diode connected load, and in the operating point the lower transistor will also in the saturation region. So what will be the current equation for these two MOS devices? We can write now. For that we should write in that NMOS, it will be very fruitful. See, this is nothing but half mu n Cox into W by L 1. Here VGS is nothing but V in minus VTH whole square equal to half mu p Cox W by L 2 into VGS 2 minus VTH whole square. Now see that what will be the W by L 1 by W by L2 ratio. It is nothing but VGS 2 minus VTH whole square by V in minus VTH whole square. Now if we want to get a gain AV equal to 10, so what will be that VGS minus VTH by V in minus VTH whole square, we can calculate. it is nothing but 100, because this is gain is root over of, sorry, 10. Okay, this is nothing but W by L1 by W by L2, which is nothing but 10. Now for take for a given MOS, if Vin minus VTH, so it is the overdrive voltage of that particular lower device, that is lower MOS, is VOB1 and upper one is VOB2, and the threshold voltage take it is 0.7 volt. Okay, if VOB1 is at around 0.2 volt, then what will be the VOB2? It is nothing but 2.7 volt. Okay, now what will be the output voltage then at the DC operating point is VDD minus VOB2. If get the CMOS 9 technology also, you readily know what will be the CMOS 9 technology also. In that case, the output volt VDD is maybe 1.8 volt, it may be 3.3 volt or so, and see what is the effect of that particular VOB2. If it is in 3.3 volt, if we take VDD equal to 3.3 volt, and if it is 2.2 volt, that is VOB2, then only we are getting voltage swing, maximum voltage swing is only 0.6 volt. Okay, so there will be very great trade-off between the output voltage swing and the gain, and the input dependency is on the GM and the gain of that particular amplifier. So in the same way, we can go to the current source load. Whatever the current source load is, why we are going to the current source loads, our main concern is to increase the gain. Okay, so we know that for the CS stage, gain is nothing but AV equal to minus GM into output resistance. Okay, if we increase the output resistance, so we can easily get the higher gain. And we also know that for the particular ideal current source, the output resistance is nothing but infinite, so we can get infinite gain. Okay, but in our analog domain, that is in VLSI domain, we realize this type of current source by MOS having a constant gate voltage. If we take the constant gate voltage, the overdrive voltage, that is VB, that is VGS minus VT, H is constant. For that case, we can get a particular constant current. We are just neglecting whatever will be the drain voltage or so. It will cover in our next class, that is the current mirror, what will be the effect of the VDS on that particular current source. And this is the constant voltage, and here we will give this input voltage, and this will be the V out. So here the output resistance of that particular MOS we can readily calculate, and we will get whatever will be the gain of that particular amplifier. Another aspect is that the triode connected load. In place of giving VB, which is compelling that particular MOS to be in the saturation region, we can use that particular VB so that this is in the triode region. And we also know that for a given VGS, if that particular MOS is in the triode region, then the slope of that particular IDVGS VDS curve is constant, this constant. Okay, so we can go to the triode connected load. This VB, this VDD. Okay, all these are connected to the ground, that is bulk are connected to the ground, and this can be approximated as this. And what is this? I have already said, whenever the MOS is in the triode region, this is nothing but the on resistance of a particular switch, and it is constant throughout the operation, because this is nothing but dependent only on the delta ID by delta VDS having VGS equal to constant. And for that case, the V out also, for any value of the V out, R on will not change. But in case of the previous case, that is in the current source case, the load is not constant. Okay. And then the last one, that is the source degeneration stage, common sources, that is very important. See, in this circuit we are seeing that there is a resistance Rs which is connected from the source to the ground. Okay, whenever if we increase the V in, the current, that is ID, will increase. Okay, if the current ID will increase, then the voltage drop across Rs will also increase. Now some part of that particular V in is nothing but also the voltage drop across the Rs also. So if we want to increase that particular V in to get higher current, and we also know that this current is, if there is no resistance, this current is proportional to this V in minus VTH. Sorry, this is proportional to V in minus VTH whole square. But whenever we have connected this Rs, we can say in our feedback point of view, there will be some negative feedback, and from our intuition we can say that if we want to increase that particular voltage, there will be increase in the current. But if there is increase in the current, the voltage across Rs will increase. So this will give a smoother relationship between the V in and the ID, because here we cannot say that this equation is valid. There is no square dependencies on the ID and the V in. This is the main factor of that particular source degeneration type of common source stage. Now I want to show whatever will be the small signal analysis of this particular stage. One other main thing is what will be the input resistance of that particular all this CS stage. You have to know that all the CS stage we are seeing that the input voltage is amplified at the gate of that particular MOS, and we know that there will be no current from gate to anything, that is there will be no current from that particular source to gate. So the input resistance or input impedance is nothing but infinite, if we say in the small signal low frequency analysis. In the high frequency there will be some impedances, we will see later. Okay. Here we have to include that is GMB term, because the bulk is connected to the source but not the source, bulk is connected to the ground but the source is not. So we have to include that GMB term here. Now see this is a coming more complicated compared to the previous one, and so we have to calculate what will be the AV and what will be the output resistance of this particular system. We see that from the previous diagram, Vn is V1 plus, oh you cannot see from that, okay, then I am writing here This V in is nothing but that particular voltage, that is V1 plus voltage across this. If there is a current, output current is I naught here, then the current through this will also be I naught, and this is Rs. So V in nothing but V1 plus this I naught Rs. Okay. Now again, whatever will be the output voltage is nothing but this voltage of drop in this R naught and this Rs, and through R naught what will be the current? It is nothing but I naught minus GMV1 and the GMVBS. Okay. So I can write here now, that is, it is nothing but I naught into Rs, it will be minus, again this V out is where I naught is nothing but V out by RD, and what will be the V1 we have calculated from the that particular equation, and this I naught can be substituted by this, and what will be the VBS? VBS is nothing but the bulk to source voltage, or bulk is grounded and source voltage is nothing but I naught Rs. Okay. If we substitute these three terms in this, there will be relationship between the V out and the V in, and from that we can readily calculate what will be the gain, which you can calculate easily. And how we calculate the output resistance is another main thing. We have to ground it, that particular input voltage. Here we have to RD should be infinite to calculate that particular output resistance. This is nothing but Vx, and we have to calculate whatever will be the Ix. From that case we can really calculate what will be the Vx by Ix. Okay, this is nothing but the output resistance, and which will, you can say that it is R naught plus 1 plus Gm plus Gmb into R naught whole into Rs. Again I am writing, this is R out equal to R naught plus 1 plus Gm plus Gmb whole into R naught plus Rs. You have to remember this equation. Now these are all the CS stage, where we are seeing that there are different trade-offs between any performances to meet a particular specification. There is a trade-off between the linearity and the gain, there will be the trade-off between the current, there will be trade-off in the input voltage, that is biasing point, and the GM, and so and so. Now I am going to the source follower. We know that to achieve a high voltage gain for limited supply voltage, the output load should be as high as possible, I have already said. But how it will drive a low impedance load then? To drive a load into a low input impedance load, the solution is we have to use a buffer stage having a high input impedance, so that the CS stage can see the high input impedance, and the low output impedance, so that we can readily drive that particular load. Okay, and this is called this can be implemented or realized by that common drain amplifier, that is nothing but the source follower stage. Okay, this is the source follower stage small signal model. First one is the small signal circuit for the gain calculation. We are seeing that it may be seemed like same as that particular source degeneration type, because there is Rs, but what is the difference? From that particular CS stage, the output is taken from the drain, here it is taken from the source. Okay, from the previous circuit we are seeing that the input voltage, that is this input voltage is also fed to that particular gate. So the input impedance is very high, that is in the small signal low frequency model it is infinite, but the output resistance is not very big. Here it is seen that output resistance is nothing but 1 by Gm plus Gmb, and for that how we go to that particular decision, that is R0 will be that we can see from that particular low frequency model, large small signal low frequency model, and that case we are seeing that this is the main circuit, the small signal circuit, from where we can readily calculate what will be the output resistance, and it is nothing big, that is if we neglect the Gmb term, it is 1 by Gm, and which is nothing big. Now what will be the drawbacks of that particular source follower? Main thing is the non-linearity. Why this non-linearity term is coming? See here, what will be the equation of that AB and the R0? If we see that there is a term Gm, and which is again depend on the input voltage, okay, and there will be non-linear relationship in the input voltage and the Gm. One other main factor is the bulk to source voltage. We know that bulk to source voltage will affect the threshold voltage also. So we cannot use the constant threshold voltage, so we cannot use the constant VOV again. So there is another nonlinearity, because this VBS term has also nonlinear relationship with that VTH. Okay, so there are the two different nonlinear problem with that common drain amplifier. Again there will be the voltage headroom problem, that is nothing but the voltage swing problem, as it is same as the common source stage. And there is another problem, it may not also good for the impedance low impedance driver, because there is a problem with that particular voltage headroom problem. That is the same problem whenever we want to drive a transmission line, that is in the antenna perspective, then it not so very good amplifying or as a buffer stage. Okay, see in the previous slide, this here there is a problem with that source to bulk voltage. Okay, there is a problem with the nonlinearity with the VTH constant. Okay, so we can readily alleviate that by using that V and VB, that is see that these two NMOS PMOS, that is called the push pull type of the amplifier type, where we have seen that NMOS the way we are using both of the PMOS, and the upper PMOS have the bulk readily connected to that particular VDD, and for the lower case it is connected to the higher voltage in the three main that is the source, drain and the gate. Whatever will be the higher voltage, the bulk will be connected to that particular node, and from that case the nonlinear dependencies on the VTH on the VOV term can be alleviated more or less. So I am going to the common gate stage. What is the common gate stage? For both cases of the common source and the common drain, we are fed that input voltage to the gate, where the input impedance is very high, that is in low signal small signal case it is infinite. Okay, but whenever it may be necessary for the specification point of view, the input impedance may be low, then what we have to do, we have to have this type of common gate stage, where we have introduced that input voltage at the source region. And from our diode connected load, we have already seen that if we apply a signal from the source region, the input resistance is not so very high, that it is not so infinite, it may be 1 by Gm or 1 by Gm plus Gmb also. Okay, and for that reason we have introduced this common gate stage. Okay, and see how this type of the transfer characteristic is coming. In the common source stage, we have increased from 0 to VDD. In this case, for our easily understandable, so we have decreased this input voltage from the VDD to the ground. Okay, if the input voltage is high, that is Vin is high, it may be equal to VDD, and VB it is not very equal to, that is it tends to VDD or lesser than, and it may be tends to VTH to make this transistor in the saturation mode. So whenever this input voltage is very high, for given VB, this MOS transistor may not be on. That is, whenever this VDD greater than this VB minus VTH, then the MOS transistor may not be on. So this output will be connected directly to that VDD up to whenever this V in greater than VB minus VTH. Whenever this VDD, V in is less than VB minus VTH, the transistor will be on again in the saturation region, because this output voltage, which is nothing but the drain voltage, will be, as it was high, so it will always turn on into the saturation mode. And whenever we want to increase this V in, decrease this V in, the output current will be increased, and so the output voltage will be decreased. And from the same relationship, that is, the output voltage is nothing but V out into VDD minus IDRD. If we decrease this V in, then the gate to source voltage will be increased, and so the current will be increased, but this VDD minus IDRD, that is the output voltage, will be decreased. And at a particular point, that particular MOS will go to the linear region, and this type of characteristics or transfer characteristics will obtained. Now see, in case of CS stage, for the low input voltage we have the high output voltage, and for the high output voltage we get the lower one. But in case of this, the common gate stage, we are getting this type of transfer characteristic, which cannot be used as a digital inverter. Okay, but we get this region where we can get the amplification, because here also the delta V out by delta V in is greater than 1. Now for the small signal analysis, we are getting this type of circuit, that is a small signal gain and the small signal input impedance calculation. Okay, we are not going to the detail how we are getting this type of circuit. You can understand if you understood that particular common source small signal model, and from this model we can readily achieve this type of gain and R in. Now see what will be the R naught. I want to draw this circuit to get the R naught. See, this is again nothing but the obtaining the output resistance of a source degeneration state. So we can readily again write that this is nothing but R out equal to R naught plus 1 plus GM plus GMB whole into R naught this RS. Again in our next single stage amplifier level, we can use this type of small signal circuits to obtain same this type of equation. Okay, now I am going to the cascode stage. This is very important stage in our VLSI design. I cannot finish, sorry, I have to take thing 130. Not till 1 not 30, I am saying that I have to take 1 hour and 30 minutes total. It's mandatory. Sorry. So I can go on briefly, but it will become more informative then. I know that till now it is informative, but still it will be more informative than these slides. Okay. What? Okay. In our Cascode stage, I have said already, na. I have to cover 1 hour and 30 minutes, so I cannot do anything. Yeah, 11:30 to 1 p.m. up to. I cannot do anything. Please keep patience. It may take more or less time. Please. Two main common. Excuse me. Please. Two main single stage amplifier are still remaining. That is one is cascode stage, another is the regulated cascode. Please keep patience. In the cascode stage, we are seeing that there is common source stage is cascaded through by this common gate stage, where through by the common source stage we are converting this input voltage to that current, and this current is fed to that particular common gate stage. Okay, and this is the transfer characteristics of this cascode stage, and the main thing for this cascode stage is its property. This, the maximum voltage gain is roughly equal to the square root of the intrinsic gain of the transistor, that is, it is nothing but square of Gm R naught. That is a very important thing. And the output impedance is also high, and another main property is the shielding property. What is the shielding property I want to define? See that I have already said the output resistance is very high and giving the gain equal to Gm R naught whole square. If the output resistance is very high, so if there is any perturbation at the output voltage, then this perturbation will reach at the node that is called the X node. Here will be very less because output resistance is very high. This is the main thing of that cascode state, that is called the shielding property, and it can be used in our op-amp design or the cascode current mirror. This is the main property of this cascode stage, and this the output resistance is increased due to this upper one, that is the common gate stage. So if we say that if we increase or cascode or the stacked more and more common gate stage, then what will happen? So we can get more and more output resistance, but the main trade-off is this: the output voltage swing will be more less and less, because in this particular simple cascode stage the output voltage swing is nothing but 2 VOV, that is overdrive voltage of these two MOSFETs. Okay, if you stack more MOSFETs, that is in this left hand side equation circuit, that is VV2 Vin, then it will become 3 VOV. Okay, this is the main thing. This is nothing but the cascode current source, so I am not going in that. Then this is the folded cascode. This is very important for the op-amp design, and here we are seeing that it is not necessary to use the same type of MOS devices for the cascoding and for the input stage. If the cascoded stage is the PMOS, then we are obtaining this type of right hand side circuit. If we use the PMOS as an input stage, we get this type of cascode stage. Okay, the main thing is that the incremental voltage or incremental current, as the small signal current, is folded up in case of the right hand left hand side, and it is may be folded down in case of the right hand side. So it is called the folded cascode from that point of view only. And the same property of that, the shielding, output gain, gain and output resistance is same here. Now this is very important. There is a regulated cascode. It is very important circuit in our VLSI domain. See, whenever a simple cascode circuit with the gate voltage of the cascode transistor being controlled by a feedback amplifier, because in that our cascode stage, see that this is that this VB. Whenever this VB is obtained by a feedback amplifier, then it is called nothing but the regulated cascode. See in that right picture, here this is the that particular cascode common gate stage. This is the input common source stage, and this common gate stage, this gate voltage is obtained by this transistor, and this transistor is biased by this constant current source. This is I1. Whenever there will be some perturbation in this particular voltage, that is, you can say that due to the lowering of the current or hiring of the current, that is I naught, there will be the voltage will be decrease or increase in that particular case. Whenever I want to draw, sorry, no need to write draw this, see this particular large signal behavior of that regulated cascode. This is the V naught and this is the VG2, that is the upper one gate voltage, that is this gate voltage of this particular MOS. Whenever this voltage output voltage is VTS smaller than gate voltage, what will happen? It will go to the triode region. Okay, but if we go beyond that, in simple cascode, the transistor or amplifier will not work in the simple cascode stage. But here we see that whenever it will decrease, the output current we want to decrease. Okay, if the output current will decrease, here the gate voltage will also want to decrease here, because there will be some drop in this particular MOS. If this gate voltage will decrease, as this current is same, that is constant, so from that challenge band modulation effect, there will be the another 1 plus lambda VDS term. If the VGS is going reducing, this VDS term will increase to increase this VG2. So we can get the higher current also, that will not affect that particular output voltage swing or output voltage impedance. So this is the main thing of that particular regulated cascode. See, this particular RGC is nothing but the regulated cascode, or OBC is nothing but the optimized simple cascode stage, optimized bulk bias voltage. Okay, here for the same VO mean is nothing but that is a 2 VOB in same case, or both cases, that is RGC and OBC. For the same VO mean, we are getting this type of higher value of the output resistance. Okay, and if we want to compare these two stages, that is regulated cascode and this is optimally biased cascode, we have to calculate for the same VO mean. So this is this, and the another main thing is that the minimum output voltage is lower 30 to 60% for the same output resistance, and the output conductance C, and the feedback capacitance lowered by the 100 times. Now this is the single ended voltage amplifier RGC. I am not going to this because we have to analyze very cumbersomely this, not yet over. Now this is the fundamental for the frequency analysis. Now up to now we have neglected all the bulk to drain capacitance on whatever the capacitance is in that source in that particular circuits, but we have to take that particular common source source to bulk, source to drain, etc capacitances. So we have to take that particular capacitance, then the gain whatever we have calculated for the CM for the CS case, that is nothing but the GM or not, that is output resistance, is nothing that we have to calculate the different node capacitance, and so I can directly go to these two different topology or two different approach to get this type of high frequency analysis. So in the left hand side we have taken different type of capacitances, that is CGA, CGB and CGD, to get the whatever will be the effect on that particular DC gain, and this is the high frequency model of that particular CA stage. This is from this we can get the exact analysis of that high frequency model, and we are just a approximated model. The another main thing I have to cover this is the Miller effect. By introducing Miller effect I can finish, I think. That is a very important. What is the Miller effect and what is the Miller theorem? Firstly, take here. See, from the circuit theory point of view, it is a node between these two, that is X and Y, there is a impedance, that is Z. Okay, so we can approximate this whole circuit to that lower one. Now I have to calculate what will be the Z1 and Z2. I can directly write this Z1 is nothing but Z by 1 minus, if this is a node voltage, Vi by Vx, and Z2 is nothing but 1 minus Vx by Vy. So why we are calculating that? We will go to the next analysis. Here the C1 will be, now see, this is the, in the previous slide I have written that Z1, that is the impedance. So what will be the impedance now? That is C1, or impedance of C1 will be 1 by C1s equal to 1 by CFS into 1 minus gain of that particular node, that is Vx by Vy by Vx, is nothing but minus A, equal to S into Cf into 1 plus A. So C1 is nothing but Cf into 1 plus A. Similarly, we can calculate C2, which is nothing but Cf into 1 plus 1 by A. For the high gain amplifier, that is if A is very greater than 1, so in the last case we can approximate C2 as nothing but Cf. So why we are calculating this type of Miller's theorem? We have to know, because see, in this common source stage, that is in the left hand side circuit, see that there is a CGD. Here this is connected to the input to the ground. Here there will be some path from this way and there will be path from this way. There are two different paths from the input to the output. So we have to split this capacitor, or we can go to this type of Q-Versum analysis. So this is the two different approach. If we can break this CGD in that by Miller's theorem, because we know what will be the gain from this to this, it is nothing but the GM/RD, that is RD will be the output resistance of that particular case, or R not is specifically said. So for that case, there will be another parallel capacitance here, that is will be CGD into 1 plus GM/RD, and here it is nothing but the CGD. This is the nothing but the small signal high frequency model. Now this is the bandwidth comparison of that particular different type of stages, that is CS, CG and CD. For the CS case, due to that Miller effect, that is the feedback case, the poor frequency response it will show, and for the common gate stage there will be no frequency Miller effect, so we can get the good frequency characteristics. Okay, so we can opt for this AC behavior of the cascode stage. That is very important, and don't see this type of circuit. I will see that particular cascode stage. See, for this particular input MOS, what is the effect of the CGD, that is the coupling capacitor from the input to that particular node X. Okay, now what is the input resistance of this CG common gate stage is nothing but 1 by, this is the M2 transistor, 1 by GM2 plus GMB2. Okay, and the transconducted parameters of this MOS is nothing but the GM1. So whatever will be the gain from this input to that particular X point is nothing but AB into minus GM1 by GM2 plus GMB2. Okay, so whenever we just split this common CGD capacitance in this particular node and in that particular node, the effect is very small, because if this transistor and this transistor have the same type of size, so we can approximate GM1 and GM2 be the same, and for that case we can neglect, or this effect of the Miller capacitance is very negligible, and for that case it may be at around equal to 2 or so, because the C1, or you can say the C in, is nothing but CGD into 1 plus AV, where AV is nothing but approximately equal to 1, because it is 1 by 1 plus eta. It may be approximately equal to 0.2 in our CMOS line technology, so we can neglect that. So C in nothing but the CGD, 2 CGD, but in case of the common source stage, we get the very higher gain, that is GM or not. So this type of Miller capacitor effect is mitigated here. Okay, now thank you very much.